Hello, everyone. My name is Alisher. I'm a graduate student at Department of Chemistry, Biochemistry, DTA, and it is my pleasure to present at the Discover Symposium for the fourth time in a row. Today, I wanted to share some work that we do at our research group led by Dr. Sherry McFarland. And the topic of my presentation is the applications of photoactivated metal drugs for cancer therapy. The main objective for our group is to treat cancer, and we study alternative cancer treatment approach called photodynamic therapy. So here's how it works. A person with cancer receives a drug called photosensitizer, and over a certain period of time, cancer cells, they absorb the drug, and later, once cancer cells with absorbed drug are exposed to light, light causes photosensitizer to generate reactive molecular species. Usually it's oxygen species, to kill cancer cells. And so far, FDA approved only the organic-based drug called photofrin. Here, I wanted to present that currently our own developed metal-based drug called TLD-1433 is undergoing phase 2 clinical trials against non-muscle invasive bladder cancer. And we have 79 patients treated so far, and phase 3 is not needed. But in general, TLD-1433 is the ruthenium-based polypyridyl complex with the oligothionyl chain tethered to the functional ligand. Objective of our current work is to synthesize, characterize, and evaluate the newer class of the ruthenium complexes, the same polypyridyl. And here, notice that we have a 5' substitution compared to the substitution on the TLD-1433, which is a 4'. And in general, the current work tested a family of 7 compounds, starting with the tris homoleptic, the phenanthroline substitute, and the ruthenium with 0 thiophene and up to 4 thiophene. Here's the synthetic scheme on how complexes were obtained. We employed the microwave-assisted irradiation, which helped us to save the reaction times and shorten them up to 15 minutes for each compound. And we obtained tris, fen substituted, and the ruthenium with 0 thiophene to 4 thiophene. And we also converted all of our complexes to the PF6, from the PF6 salt to the chloride salts, since chloride salts are more biocompatible for testing. Here's how we characterize all of our compounds, making sure that we obtain desired product. We use the 1D and 2D nuclear magnetic resonance for NMR techniques, and all of the proton assignments were done with the help of the technique called COSY, correlation spectroscopy NMR. We later recorded absorption spectrum for all of our 7 compounds. So to simplify, we indicated the main bands on the spectrum and highlighted them as intraligand processes, intraligand charge transfer, and metal to ligand charge transfer. And also, we performed the excited state absorption properties, is recording the absorption profile while the molecule is being in an excited state. And with the ruthenium with 0 thiophenes, we only observe this kinds of depopulation around 450 nanometers, while for the complex with 4 thiophenes, we not only observe the same depopulation, also observe the population of the excited state, which is indicating the charge transfer within the thiophene chain in a drug. And later, this was confirmed by the photobiological evaluation, where ruthenium with the 4 thiophenes was the most active in the series, where the EC50 values were reaching about the nanomolar activity, while the phototherapeutic index, which is the ratio of the dark EC50 to the light EC50, also reaching the numbers of 400,000. So in other words, the higher the PI value is better. And all of our complexes were non-toxic in the dark, which is the good sign of the photosensitizer. And to sum up all said above, we synthesized a new family of the compounds. We indicated the ILCT state is the key to achieve the biological activity. And once we increase the number of thiophenes, we lower the excited state and make it more accessible upon photoexcitations. And I want to thank our funding agencies, the Department of Chemistry at UTA, College of Science. And if you have any questions, feel free to reach out on social media or check our website.